Hi everybody, welcome back to this course on Internet Technologies. I'm Vardan and today we'll be studying about Diffie-Hellman key exchange. Let's start with a simple question. How can two people who've never met and who are communicating over an insecure network like the internet agree on a shared secret key? Back in 1976, Whitfield Diffie and Martin Hellman came up with a brilliant solution. It's called the Diffie-Hellman key exchange. Unlike the RSA algorithm, which encrypts a secret key using a public key, Diffie-Hellman allows two parties to agree on a shared secret without actually transmitting the key itself. And incredibly, it does so without using any encryption. The idea is purely mathematical and it's based on something called the discrete logarithm problem, or DLP for short. So it's a problem that is incredibly hard to solve, especially with large numbers. But do note, Diffie-Hellman is not used for encryption or authentication. It's only used to agree on a shared secret key. Once that key is in place, you can then switch to symmetric encryption methods like the AES to encrypt actual data. So here's how it all begins. Two users, let's say Alice and Bob, publicly agree on two numbers. First is a large prime number denoted by n. Second is a primitive root modulo n denoted g, which must be less than n. Now what is this primitive root? A primitive root modulo n is a number such that all numbers from 1 to n minus 1 appear as some power of g modulo n. In simple words, if you keep calculating g to the power 1 mod n, g to the power 2 mod n, g to the power 3 mod n, and so on, the results will eventually give you every number from 1 to n minus 1 in some order. Not every number has this property, which is why choosing g is a careful decision. Once n and g are agreed upon and publicly known, both users pick a private number which they never share. Let's say Alice picks a number x, Bob picks a number y. Then each of them perform simple computation. Alice computes x equal g to the power x mod n, while Bob computes y equal g to the power y mod n. Now comes the exchange part. Alice sends her computed value x to Bob and Bob sends his value y to Alice. Note, they are not sending their private keys x and y. These are just the computed results. Here's the magic now. Now Alice takes the value y she got from Bob and raises it to the power of her secret x. So she computes Ka equal y to the power x mod n. At the same time, Bob takes the x he received from Alice and raises it to the power of y, that is his secret key. So he computes Kb equal x to the power y mod n. If you've worked out the math, both end up calculating the same thing, which is g to the power xy mod n. Even though they never shared their private keys, they now both hold the exact same shared key, which they can use for symmetric encryption from this point on. Now you might be wondering, if n, g, x and y all are exchanged publicly, what's stopping an intruder from calculating the key? Here's the thing. Yes, an attacker may know all of those values n, g, x and y. But what they don't know is small x or small y. And to calculate the shared key, they'd need to at least calculate one of those. So to find x from x equals g to the power x mod n, the attacker would need to solve what's called the discrete logarithm problem. Let's break that down. The discrete logarithm problem asks, given g, n and x, can you find an x such that x equals g to the power x mod n? This is computationally infeasible for a large n. That's why in real implementations, n is chosen to be at least 2048 bits long, a number with hundreds of digits. Also, we prefer using safe primes. That means both n and n minus 1 by 2 must be prime. This avoids certain mathematical attacks. So as long as good parameters are chosen, Diffie-Hellman remains secure even over an insecure channel like the internet. Now, despite how elegant and powerful Diffie-Hellman is, it does have its weaknesses. The biggest one, it's vulnerable to a man in the middle attack. Here's how. Suppose an attacker intercepts Alice's message before it reaches Bob. They can replace Alice's public value X with their own and trick both parties into creating separate shared keys, one with the attacker. In the end, both Alice and Bob think they're talking to each other securely, but in reality, the attacker is reading and possibly modifying everything. This happens because there is no built-in authentication in Diffie-Hellman. To fix this, we combine Diffie-Hellman with digital signatures or public key certificates, which help verify that a message really came from who it claims to be. Despite this, Diffie-Hellman remains widely used, especially because once the shared key is established, we can switch to symmetric encryption, which is far more efficient and faster for actual data transmission. And that's the end of this video. And in the next lesson, we'll be learning about cryptographic hash algorithms and authentication. So thank you for joining in, and I'll see you next time.